Hello everyone, today I'll be talking about the application of first order ordinary differential equation or ODEs in mathematical engineering. A first order ODE is an equation that relates a function and its first derivative. It typically looks like dy over dx equals to fxy. This tells us how a system changes. In other words, how the rate of change of a quantity depends on its current state and an independent variable like time. For real-world applications, these equations are extremely important in engineering because they help us model dynamic systems that evolve over time. For example, in mechanical system, ODEs are used to model motion like velocity under gravity with air resistance. In electrical engineering, they describe the behavior of RC and RL circuits using Kirchhoff laws. For thermal systems, Newton's law of cooling is modeled using a first-order ODE, and in fluid dynamics, they help predict flow rates and pressure change in pipes. Why does it matter in engineering? Solving these equations help engineers predict future behavior, optimize system performance, and ensure stability. Depending on the problem, we can solve them analytically using methods like separation of variables or integrating factors, or numerically using tools like Euler's method or Shkota methods. In summary, first-order ODEs are a core tool in engineering. They connect mathematical theory to practical problem solving, making them essential in almost every field of engineering. Thank you.
Assalamualaikum and good morning everyone. My name is Nurul Adriana binti Mak Fauzi, AA240253. This presentation covers our figure table on exponential growth and Newton's law of cooling. For the first part, we analyze this fish population growth from 2000 in 2015 to 3,500 in 2020 using the exponential formula to estimate future population and determine when it will reach 10,000. We learned how to find the growth constant and apply the model through notes, calculators, and tutorials. In the second part, we use Newton's law of cooling to calculate how long soup takes to cool from 100 degrees Celsius to 18 degrees Celsius. Based on early data, we review formulas, use examples, and watch videos to guide our solution. These tasks help us understand and apply mathematical models to real-life problems. Thank you.
Good day everyone, today I will be presenting a case study on exponential population growth in a protected freshwater lake focusing on the dripping fish species. In 2015, research recorded a population of 2,000 fish due to clean water, abundant food and low predation. The species grew significantly. By 2020, just 5 years later, the population increased to 3,500 following an exponential growth pattern. To model this, we use exponential growth formula. Pt equal to Po e power kt, where Pt is the population at times t, years after 2050. Po equal to 2000, P5 equal to 3,500 in 2020. Substituting into the formula, 3,500 equal to 2,000 e power 5k, e power 5k equal to 1.75 k equal to 0.1126. So the population model become Pt equal 2,000 e power 0.1126 t. This means the population will reach 10,000 around mid-2029. In conclusion, using exponential growth modeling, we can predict not only future population size but also when key milestones will be reached. This helps plan conservation strategies effectively. Thank you.
Okay, now let's move on to part B, where we apply Newton's laws of cooling to a real-life situation. In this case, a pot of hot soap is placed in a room where the temperature is constant at 20 Celsius. Initially, the soap's temperature is 180 Celsius. After 20 minutes, it cools down to 100. We are asked to find how long it will take for the soap to cool further to 80 Celsius, a safe temperature for eating. To solve this, we use Newton's law of cooling, which is modeled by the differential equation dt over t. Okay, first step we use dt over dt equal to t minus t en v. We separated the variables and integrated to get the general solution. After that, using the initial temperature, we found that C equal to 160. So the equation becomes T in the bracket T equal to 20 plus 160 E negative EKT. Next, we use to the unknown value T in the bracket 20 equal to 100 Celsius to solve the cooling constant K, which is come out to the approximately 0.0347. Finally, we substitute T equal to 80 Celsius into the equation and solve the T. The result was approximately 8.3 minutes. So the soap will take about 8.3 minutes to cool down from 100 Celsius to 80 Celsius. From this case study, we can see how first-order differential equation apply to real-life situations like temperature changes in the thermal system. By using Newton's law of cooling, we model how the soap's temperature decreases over the time and use it to make a useful prediction when the soap would be safe to eat. This kind of model is not only used in food science, but only in thermal engineering HVAC system and even forensic science to estimate time of death.
Hi and Assalamualaikum. My name is Nur Ismail Jab binti Ismail Khairul. My matrix number is AA240096. So for this part, I will talk about discussion that we have made to conclude our topic on this subject. In part A, the exponential growth model was used to estimate the population of a fish species in a freshwater lake. Using data from 2015 and 2020, the growth equation was formulated to predict future populations, including an estimate of 10,000 fish by mid-2029. This shows how first-order differential equations can model biological growth in real-life scenarios. In part B, Newton's law of cooling helped determine the time needed for hot soap to cool from 100 Celsius to 80 Celsius in a 20 Celsius room. By solving the differential equation and calculating the cooling constant, it was found that the soap would be safe to consume after approximately 8.3 minutes. Both cases demonstrate the practical use of differential equations in Both cases demonstrate the practical use of differential equations. Both cases demonstrate the practical use of differential equations in modeling real-world problems, whether in biological or thermal systems, proving that their importance in science and engineering applications. As for the conclusion, our thought through this PBL project, we gain valuable insights into how first-order ordinary differential equations can be applied to real-world problems. In part A, we model the exponential growth of a fish population, which allow us to predict future population size, an approach commonly used in ecological and environmental studies. In part B, we use Newton's law of cooling to determine how long hot soap would take to cool to a safe temperature, showing applications in thermal engineering and food science. This project not only enhanced our understanding of differential equations, but also improve our problem-solving skills, teamwork, and ability to connect mathematics with real-life situations. That's all from me. Thank you.